Hello, welcome back. We are going to start the afternoon with Yoav Artzi from Cornell.
Okay, hi everyone. Thank you for coming back from lunch. I'm surprised so many people are here. Okay, so I'm going to talk about world models, and I changed the talk multiple times. I kind of, because I felt like this, at least part of this week was, follow this like fable, this parable of the blind man and the elephant, where we're all kind of trying to fill the world model and try to say different things about it. But we're in California. And honestly, academics feel to me more like sleepwalking children than blind men. So I took a ChatGPT to the task and got something like this. So this is our world model, and this is all of us. And basically what I want to do is I want to add like, interesting. Three kind of like bubbles to this diagram. One about kind of like consistency. So if we think about the world model, we really wanted to have some kind of a consistency in the representation. One about simulation. So a world model, so there are different definitions of world models, but I think one of them uses that we would like for a world model, and it came up multiple times in the last few days, is to kind of like to roll out into the future, to imagine what will happen if we'll do things, a number of actions, and then kind of like figure out if what we want to do, what we plan to do makes sense. And the other thing is a world model should have like a really rich kind of like state representation. So the first part of the talk, I'll talk about evaluation. For consistency, I'll talk about cross-perspective spatial reasoning. And for simulation, I'll talk about manipulation planning. And then in the last part, I'll talk about state versus prediction and how we can potentially get some interesting, better state representation in Transformer. This is a really fresh results from the group, which we are still trying to wrap our head around. Okay, so we'll start with the cross-perspective spatial reasoning. This is actually something that is really rooted, I think, in a collaboration from the last workshop. So if you need to kind of like to report something. Okay, so as humans, it's very natural for us to reason across perspective. A very easy example is maps, right? What happens when we look at a map and compare it to the environment is we reason across different views and different representations. And basically, these are all different projections of the same world, of the same world state. So we can imagine that underneath it all, there is some kind of like a consistent underlying representation. So if you want a world model, arguably a good world model should be able to kind of like to do this kind of reasoning. And there is a lot of work in developmental psychology about this. So this is one example that really kind of like motivated and seeded all this work. It's from Dylan and Spelke. This specifically is from their 2018 paper, where they did this experiment with the children, where they show them a target in an overhead view. And then they ask them to identify in a different perspective. And a different perspective is they put them in a first-person view in this environment. And there is this really nice the complexity gradation in their design, because they have this it's like all triangles, but they can remove part of the walls, or they can change the angles to make them softer. So it creates a lot of interesting complexity. And generally, so this is kind of like what you see, and this is what they did is they tried different ages with different kind of like levels of complexity, and you see a very nice kind of like trends of developing this skill over age. Okay, so this is you can think about it basically accuracy. So we picked up on this design, and we used it to develop a benchmark we called a REMAP, a representational mapping benchmark, which, unlike a lot of the evaluation suits for multimodal models, it's isolated kind of like sort of the geometric core in spatial reasoning. So the objective is very simple. We are going to give you some kind of an overhead map, and we're going to mark a target, and you're going to find this target in a first-person view. Okay? So this requires mapping the allocentric and egocentric views. It requires reasoning about partial views, because overhead view is going to be much more limited, and to kind of like to align the symbolic representations from the map with what you observe in the real world. So we have two versions of it. The first version is really follow the Dillon and Spelke scenario, where we instantiate their triangles in a 3D environment. And then in order to make it more digestible for LLMs, we take different snapshots, multiple snapshots from a slightly different perspectives. And then what we do is we create this kind of like multiple choice questions. The map shows the target in yellow. Which number in the first person view matches it? So this is the target, this is the target, this is the overhead map. And you get this like multiple perspective with these numbers, and you have basically a multiple choice question. So a very simple kind of like thing to evaluate. We follow the Dillon and Spelke in their design. So we have different kind of like types of triangles by removing parts of the sides or the corners, and we have this gradation with the angles. So 6 target locations, 4 angle configurations, and 3 wall configurations. So this gives us one version. This gives a triangle version. It's a controlled and a synthetic scenario, which has a lot of grounding in the literature. In addition to that, we create another version that is grounded in floor plans. So floor plans give us something a bit less controlled, more messy, but in a way more realistic to the kind of structures that we are used to see in our daily life. And we follow exactly the same recipe. We instantiate the floor plans in a 3D environment. We take different snapshots, and we create this kind of like multiple choice question. When you get an allocentric map and 3 egocentric views with numbers on them, and you have to pick the number that corresponds to the target. OK? So this gives us basically around 7,000 questions. We instantiate all the possible combinations. We evaluate a large set of multimodal LLMs on it with some commercial models. I'm not going to show all of them. And we also do human evaluation, just to see, not only to see how we are able to, how models compare to humans, but also see that we are able to kind of like to replicate what we see with Dillon and Spelke that show that humans are pretty good at that. We are not doing it with children, and it's all down online, so there are some differences. Overall, we see that there is a very large human model gap. The average human is about 75% accuracy, and the best human is even much higher, where generally models have a very hard time kind of like crossing the random baseline, except the Gemini models seem to be pretty consistently somewhat better than it, but still much worse than humans. There's also an interesting effect of targets, whereas humans are not really sensitive to the number of targets, especially in the floor plan. We can scale the number of targets to up to 14. Models get confused very easily. So the minute they see more targets in the candidate images that we give them, so there are more options, so they start to fail much more frequently. OK. So this is about cross perspective, and now I'm going to switch to manipulation. And the kind of like to start this, I want to ask this question of if you can convert this form here, this kind of like tied rope, to this open loop there. What do you think? Yeah, OK. So what do you need to do that? Unfold it. That's like, OK, so you unfold it in your mind, right? So you have to reason specially about each of these configurations to kind of like to understand the differences between them. And then, I don't know, at least when I think about doing it, I'm kind of like visually planning in my head. What will happen when I will pull different parts and exert different powers, different forces on the tied knot, and then I have to map it to the real world. And of course, nothing works in the real world as expected, so I'll probably have some kind of a closed loop and refine myself continuously. So these are knots. Knots are very cool. They provide a very interesting test bed to kind of like fine-grained continuous manipulation. It has no confounding factors with language, which is kind of nice to isolate only the visual part. They have a very interesting and clear measure of generalization and difficulty by looking at the number of crossing. So the more crossing a knot has, it's generally considered more complex. And this allows you to kind of like to think about train test generalization in a very clear way, right? So you can think, I'm going to train on knots that include maybe 0 to 3 crossings, and then I'm going to test on knots that go from 0 to 7 crossings, so much more complex knots. If you internalize the principle of manipulating knots, you're going to generalize fairly well. If you're overfitting, then you're going to see it pretty clearly. Knots are relatively well studied, and there are a number of formalizations describing them, and that allows for a relatively easy formal verification. So we use something called Gauss code, and the nice thing about it, because if you go back to here, so this is a loop. If you want to go from this knot to something that looks like an open loop, there are actually an infinite number of configurations that you can take. So simply comparing exactly to this configuration is going to really miss the point of all I want to do is just untie this knot. So with Gauss code, you can have a symbolic verifier that really covers the whole space. So given whatever configuration, I can validate if it really gives me the target configuration that I want. And there is also some understanding of difficulty because of theoretical work. So generally, and I'm not an expert in that, so with zero crossing is an unknot. It starts to be more interesting when you have 3 crossing. Up to 12 crossing is tabulated by mathematicians. 19 crossing is tabulated by computers. And above that, it's basically an unknown territory. So we design around knots as a scenario called notchim, which asks a very simple, straightforward question. Suppose 2 knots that we show you are equivalent. How do you convert from knot A to knot B? It's a Mojoko simulation, a continuous simulation. The number of crossings, just like in knots, offers you a very clear ladder of reasoning difficulty. And the Gauss code that underlies these configurations allows you for very, very simple and straightforward and exact verification. So evaluation just comes for free. The observations are RGB images, and the actions are this kind of like 6 degrees of freedom, so basically 6 real numbers. You have X, Y, Z coordinates, so you basically grab a piece of the note, kind of like the note in a specific point, and you exert a certain power in a certain direction. So 3 numbers for the point, and 3 real numbers for the force that you exert. And it works in some kind of like, it's paced in some discrete time. There are 3 task variants. Again, kind of like giving you a gradation of complexity. So all the tasks have this. You get basically 2 knots. One is the one you're manipulating, and the other one is the target or the target shape. So you don't specify in language or any formal description what it is, what your target is. You give it completely visually. So if in the first one, in the unknot, you get a tied knot and a loop. That's the right one. The target will always be a loop. And you basically have to unknot the knot on the left to the open loop. In the second one, you do exactly the reverse. So it's a bit more complicated. You get a loop, and you have to tie it to some kind of like a target configuration. Now, of course, because of the Gauss code, you don't need to reach this exact configuration. All you need to do is to reach the kind of like the configuration of crossing that the target gives you. Yes?
Just to understand, basically, if you take 2 pieces of rope and you cross them on top of one another, that's...
You get a crossing. Yes, exactly. So here you're not going to get, for example, in this example, if you manipulate this open loop, and this is your target, you can get to here. This doesn't exactly look like this one, but it has the same Gauss code. So a model really has to kind of like figure out the equivalence class that is underlying it in formal representation that it's never exposed to. And the most complicated of the 3 is a conversion. You get 2 knots, and you have to convert one, and you have to convert the one on the left to the one on the right. Okay? So we tried, I mean, most of what we did with this benchmark is we tried to train it on, with RL from scratch. When we did this work, I don't think the models were mature enough to give you a kind of like any meaningful evaluation as frontier models, and I'll show one example of what you get in this scenario. So what we did is we focused on just training from scratch, and there are kind of like two classes of methods here. So PPO is a very kind of like vanilla RL method, whereas Dreamer and TD-MPC2, they have some sense of world model inside. In Dreamer, it's implicit. The TD-MPC2, it actually acquires a world model and rolls out its own world model as it's doing test time. And generally, you see that like for very simple scenarios, these methods do relatively fine. But for more complex ones, especially when the number of crossings goes above 3, the performance basically deteriorates to almost 0. Now, what happens when what happens when you go for a MLM? So during so when we presented this at NeurIPS, one of the people who came to the poster went and tried to prompt Google VO with this, and what you got was something that it's pretty short. So you want to convert from this to this. This is the exact prompt that I gave at the beginning of this section. It's pretty cool. I'm not sure it's really doing what it's supposed to do. It's something like this. Now I don't have it. I wonder if that's going to work. Yeah, there is sound as well, which is really cool. I tried to run it. Yesterday on some of the more recent models. It goes even wilder. It doesn't get closer to actually solving the task. I didn't add this because I'm not sure what I'm supposed to kind of like share with these Google models nowadays. Okay, so this summarizes this part. So evaluation. So it's kind of like two aspects: consistency and simulation with these models. And we're going to switch gears completely now and talk about representation. And basically kind of like distinction between state versus prediction in LLMs. Okay, so transformers, we all know transformers, but just to kind of like put us on the same page, it's the most common architecture in LLMs. The way transformers work, it is probably the millionth time you heard it. We give it a token, and each time step we compute these representations going up the transformer, and then we output the next token to predict. We then take this next token, and we continue. We give it to the next time step, get the next token, and so forth. And during this process, what we are doing is we are computing all these representations, and these representations are going to be, so the representation in specific time step, they are used to two functions. They're used to predict the token at like that specific time step, and they're also used to predict future tokens. Because we have this self-attention mechanism, we're going to use these earlier representations when we predict these later tokens down the road. So there is a prediction function, right? We want to predict what is the next token that we're doing. But there is also kind of like a state function where we want a state representation that will be good for the future, for future tokens. And we can think about the kind of like, we can think about doing as from the learning perspective. So this is our, this is the log entropy, the cross entropy loss of LLMs, and we can basically, if we take out the parameters and we kind of like freeze them at every time step, they're all the same parameters, but it's in a way it's similar to how we talked about RNA in the past. So we have the parameters for step 1, step 2, and so forth. We can break the loss, the gradient that we get for these parameters, to kind of like two sources of learning, if you would like. One source is coming from the immediate prediction, like how good I am at predicting the token at my current time step. And another loss is how did I contribute to predicting the future tokens that will come later on in future time steps. Okay? So we have these like two roles that are basically entangled together in these representations. They have to be good for two things: predicts the next token and be useful for predicting the future tokens later on. So given this kind of entanglement, we hypothesized, we call it the state prediction separation hypothesis, is that then these two roles they compete when they are forced together into the same representation. So if we disentangle them, we'll potentially get better language models. So instead of having this single representation that takes the information for the prediction and takes the information from the state, we would like to break it apart into two representations. And hopefully it will give us better language modeling, but also it will give us a stateful representation that is really focused on kind of like the state rather than making the exact decision of the token that we are going to output now. Okay? So we created this SPS transformer. It's a very, very simple modification of the original transformer. So what you do now is instead of like making like a single kind of like stream of prediction to create the next token, you're going to have two streams of computation that are paired together and happen concurrently. So you get now for every token, you get this kind of like body that is a dummy token with it. And you go and they go up the transformer together. And then from the from the time step for dummy token, we're going to predict the token. So we have two streams here. The stream on the left is going to be a state stream, and the stream on the right is for the prediction. And we continue with this like dual stream for basically to predict the entire sequence. Now, importantly, and this is why these two streams are colored differently. The stream that the first one in the pair, that's going to be our state stream. We're going to keep it in the KV cache in order to predict tokens in the future. Whereas the computation that took place to predict the next token, they are going to be discarded. So they're just simply not going to be added into what is called the KV cache in transformers, and that practically means that future tokens are not going to see them. So to predict X6, I'm going to see these opaque blocks, but I'm not going to see these kind of like dashed white ones. They're just going to disappear. Okay? Okay, so it's pretty straightforward. Now, then we train completely the same. Nothing changes in the transformer itself. So we did a bunch of like pre-training experiments. We pre-trained a number of LLMs on 20 billion tokens using a pretty standard corpus of raw text. We did 4 sizes. I'm going to show 4 sizes now. We are just at the end of running the 1.5B one that takes a while, so wasn't ready for the talk today, or for the submission to NeurIPS. We use a GPT-2 architecture with some modernizations, and we are going to discard the KV cache for the kind of like for the ephemeral for the predictions time steps after 64 tokens. So we keep some window where we keep all the information for like short-term dependencies. So the main result is basically kind of like captured in this graph. So what is this graph? This graph is basically gives you a dependency between the number of training tokens. So this is the x-axis here, and this is the amount of data that you are seeing, and the loss and your training loss. So this is just the next token prediction loss. This is the likelihood of our training data. And I have two. And so lower on the loss is better, right? Okay. We have 2 graphs here. The green one, this is our SPS transformer trained on up to 18 billion tokens. And the black one, this is a standard transformer, just out of the box, a regular transformer with the same architecture trained on up to 36 billion tokens. So what you see is that there is like a significant gap here for on training loss, given the same token budget. And even if you double the amount of data you train on the standard, you're still not able to match the training loss that you can get once you separate the 2 functions. Okay, now there are a number of confounders here that should.
How far away do you look whether you're useful for prediction?
How far?
How far away? Like, okay, not the next step. You say you have 2 parts to the loss. One is prediction of the next step, and the second one is how useful you are for future prediction.
Okay, so this is great. So the loss is the same. The decomposition of the loss that I saw was just for kind of like explanation reasoning. It's the same loss. Does that make sense?
So how far away does it actually, in principle, affect?
Okay, I'll show you some. So it's an empirical question. I'll show some results. Yes. 5 minutes. Okay. So you have a question. Yes.
What about the storage and training time?
So storage is the same, training time is higher, and so this is bring us to the confounders, right? There is added costs that are involved in here. So this is our SPS transformer. Now something that clearly you're seeing here is that, like, right, I'm actually doing two steps for every step in the original transformer, in the standard transformer. So flop-wise, I'm burning many more flops, but in generation, it actually doesn't matter that much. And the reason it doesn't matter is because these two steps are done concurrently. But training time, it does take longer, and I'll show you a GPU hours plot in a second. But as far as computation, there are kind of like two other alternatives that we can measure against. One alternative is what we call a delayed state. So rather than so now we are going to keep in our KV cache the same stream that we use for prediction. So we have the same number of flops as SPS, but we're going to keep in the cache what actually the representation that we use for prediction. Okay? And the other one, this is kind of like we're going to double the memory and double the flops. So just basically add this kind of like almost like these weight tokens that are happening in some work. Okay? Okay. So there's no surprises. You increase the flops, you increase the memory, you get better performance. So what I'm showing here, this is large, and this is the kind of like the smaller models. In black, it's at the top here, it's training tokens versus loss, and at the bottom, it's GPU hours versus loss. Right? So time and loss, data and loss. In black is the standard, and in orange, it's a delayed state. And in blue, it's like the one that 2x memory. And what you're seeing is that, yes, by doing the delayed state and 2x memory, it's more compute, we are able to improve over the standard, but with SPS, the performance is still better, which means the specific separation actually is meaningful and beneficial. By the way, what you're seeing here, this kind of like thing here, it's the cooldown. So these are models under cooldown, and cooldown preserves the advantage. And here it's a bit hard to see, but this line here is what happens when we give it more tokens. And at the end, the SPS, after a while, actually crosses, even when we look at GPU hours, even though at SPS is training time, it actually takes many more flops. Now, another thing that I think Michal asked about, what happens with, how much actually information do we get from the future for SPS compared to the other ones, because that's actually what's meaningful for the state. So this, what we're measuring here is this ratio between the gradients we get from the future for a kind of like a specific distance. So this is our, so this is K. Up to compared to kind of like what we get from the current time steps. Okay? And what you're seeing is the most important thing here to look at. So this is like, this gradient ratio. The higher it is, it tells you that the gradients come from the future are relatively have a heavier weight compared to the gradients coming from the current time steps. And this is like, this is the relative offset. So this is like how far you. So the important thing here is because the difference, and then I'm out of time, the difference between the SPS and the standard, the SPS relatively retains a much higher proportion for the loss that's coming from kind of like these distant gradients compared to standard, which decays very, very fast. Okay, so I'll just finish with the credits. So the first project about dual perspective was done by Selina Chang and Ann Wu in collaboration with Eunice from here, I guess, from Berkeley. The NotGym was done by Zoe, and the SPS work was done by Giovanni in collaboration with Nathan and Chiante. Thank you very much, and I think I'm just on time. Yeah.
Yes, the SPS is really, really neat. You're decomposing into something to do next token and future. That seems like, why that decomposition? Could you decompose into, next step, 10 steps in the future, 100 steps, like more intervals, longer spaced intervals? Do you think that would be?
I don't know. So we're just starting to look at things. We're trying with several things. We also see some kind of improvements when you're actually not only separating the stream, but also separating the parameters of the streams. So I think the space of things to experiment there is fairly large. And yeah, your intuition is good. You can. So I've been thinking in that sense of almost like a. So you know the Matryoshka architectures where you have different parts of the embeddings. So you can almost think about keeping only certain number of heads for farther away because you need less information compared to more dense information for near decisions. So you slowly decay the path. So it can also give you the very nice compression effect, but we didn't try it yet. Yeah.
I'm curious how much of this is coming from predicting 2, 3, or 4 tokens, kind of related to your question, versus just the future in general. Have you seen an advantage? Is it can you try to break that up and say 5 tokens forward is the sweet spot, or 100 tokens forward?
So in the last slide I showed this gradient, right? So I think what you see there is that there is something that comes from the near future, but then you have significant amount of the gradients actually coming from farther, and we measured all the way to 500 tokens in the future. So there is definitely a decay. There is no doubt about it. But it actually retains a much higher learning signal from, as far as the gradients at least, coming from the future compared to standard where it decays to a very low percentage very fast. One more. Okay.
So the state token, is it learned?
The state token, it's a new token. We learn it's embedded.
And do you reinitialize it every step, or do you carry over? So is it the
same token? That's what you're asking?
Yeah. Is it the same token across time steps?
It's always the same token. Yeah.
And if you tried carrying it over like a proper state, in a sense like an RNN,
it will be very hard to train, right? Because then you have time dependency during. But there is a lot of interesting work. The training the RNNs, yes. So there is actually a lot of interesting work happening in breaking this time independence. There is a lot of training costs, but there is actually interesting behavior. I saw this some psychologist from Stanford gave a talk at GDM a few months ago, and showing some interesting, because then the rationale was that the human brain doesn't really have this constraint. So
yeah, very good.
Yeah.
Thank you.
Thank you so much.
Thanks, Shirley.